it anywhere you see it now. And it's the signature of complex dynamical systems like climate. Systems or networks don't exhibit just any kind of behavior. Instead, they have limited, discrete states that they exist in. A simple, almost overly simple example is a brick. A brick can either be standing up or laying over flat. There's no in between. There's no stable in between states. It's either up or it's down. And these states undergo something called phase transitions, rapid transitions between states at things called critical thresholds, that's a technical term, or tipping points. So imagine the brick is standing up, you push it just far enough and it hits a tipping point and it falls over very quickly. That's a tipping point, phase transition to a new state. A more complex example of attractor states and tipping points is waking and sleeping in us. You all right now are awake. At some point later today, you will fall asleep very quickly. There's not much in between time. You may be drowsy for a minute, but you fall into that sleep state. And at some point later on, you will wake up. Perhaps when the alarm goes off, you move quickly from a sleeping state to a waking state. A third example is camels. Particularly camels, whereas humans regulate our temperature at 37 degrees centigrade, that's 98.6 Fahrenheit, camels regulate their temperature at two different states. During the day, they regulate at 40 degrees centigrade, that's 104 Fahrenheit. That reduces sweating. They let their temperature drift up to the ambient warm temperature of the desert. They don't have to sweat to keep cool, and it saves water. They're desert creatures. At night, it's cool in the desert, so their temperature undergoes a phase transition down to 34 centigrade, that's 93 Fahrenheit, and that saves energy. They don't have to keep themselves warm. If we reached 104 or 93, we'd be very, very sick. Camels do this every day. A fourth example of attractor states are Gaia's three climate states. It has three: very cold, warm like now, and hot. That's it. There's no in-between states. Cold is the ice ages, and there's been a bunch of them over the last few 100,000 years. We're currently in a warm interglacial, that is between ice ages. And we've been oscillating between ice age and interglacial for about 2 million years, about every 100,000 years or so. Every once in a while, during an ill time, Gaia pops into a very hot state that we often call a PETM-like state. And PETM is an acronym that stands for Paleocene Eocene Thermal Maximum. Those are geologic periods a long time ago. The last time one of these happened was 55 million years ago. And unfortunately, that's where we're probably going to next, in the next few decades. It's a very hot state in which Earth will eventually be iceless. We'll lose the ice on both poles. Now, I want to shift over and talk about something called non-equilibrium thermodynamics. And again, this is way easier to understand than pronounce. It's a horrendous name. For simplicity, we can simply call it NET. This is the newest version of the science of energy. The science of energy is called thermodynamics. It was invented in the 1850s and before that. It deals with energy types like electromagnetic energy that includes light and heat and chemical energy. The main idea of NET is energy gradients, and specifically in energy gradients, energy flows downhill, which dissipates, that is, disperses the gradients. Now, you can think of a gradient as a situation when you've got more stuff in one place than in another. And so if you've got more energy here than here, the energy is going to flow downhill, metaphorically speaking. So here's a diagram. You've got more energy on the left side than on the right side. And the energy flows from high energy to low energy in this direction. Automatically, the lights in this room are flowing out from the light bulb. Heat from your body is flowing out from you. It's a gradient. And so non-equilibrium thermodynamics studies how these gradients dissipate over time. As an interesting thing that we've discovered in the last 50 years or so, if there is matter present in an energy gradient, and if the matter is of the right kind, And if the energy is of the right kind, then that matter in that energy gradient will spontaneously self-organize into a more complex state. And that complex state is called a dissipative system, because the system, by self-organizing, is dissipating energy, it's dispersing energy through itself. We are taking high-quality food energy and dissipating it through ourselves as heat. The heat is the waste coming out the other side. But in the process, we dissipate the energy gradient more effectively, which is in congruence with this main idea of non-equilibrium thermodynamics, which, by the way, is a new version of the very famous law in thermodynamics called the second law of thermodynamics. And it's been said that if your pet theory in science violates the second law, then woe be your pet theory. It won't work. The second law of thermodynamics is unbreakable. So this idea of self-organization goes with the second law of thermodynamics. The second law of thermodynamics actually dictates self-organization because it dissipates energy gradients more effectively in accordance with the second law. All forms of life, including cells, you, ecosystems, and Gaia, are dissipative, self-organizing systems. And this gives us a way of looking at how life forms work over time. Now I want to show you some examples of self-organization, starting with some simple ones. Vortices or whirlpools are a great example. Pull the plug on the bathtub, and the water self-organizes into this marvelous little whirlpool, which makes the water drain out of the tub more quickly. I learned that as a kid very early on, that if in my nightly bath, when the plug was pulled, if I used my foot and disrupted the whirlpool, I could stay in the tub longer because it took longer to drain out. But the whirlpool makes it drain more quickly. Tornadoes and hurricanes are vortices as well, but in this case they're dissipating heat energy from the surface, either the land or the oceans, into the upper atmosphere more quickly. And they're very destructive in the process. Here's an example called convection cells. This is another example of self-organization. You're looking here down on a little flat-bottomed glass dish that's filled with some fluid. It can be water, more commonly it's an oil of some kind, and that dish is sitting on a hot plate. So you've got a heat gradient coming from the bottom of the plate into the top and out the top. So you've got a gradient of heat energy. And as you turn the hot plate up, you'll notice that something happens at a particular gradient, particular level of the gradient. You move from just fluid into these little cells that self-organize. And if you were standing in the middle of one of these little cells, here's one, here's one, here's one. If you were standing in the middle, one of these little black dots, what you would find is that hot fluid is flowing up around you. It's releasing heat into the atmosphere. It becomes denser and it flows back down around you, down to the bottom of the dish, picks up more heat and comes back up again. So it's this flow pattern this way. And there's another one over here, and another one over here, and another one over here. Those convection cells are dissipative structures. And if you reach in and pick one up, it's nothing but fluid, but the fluid organizes into this little flow pattern. There's actually 3 different attractor states. This is the first one. It actually looks more linear at first, and you turn the heat up a little bit more, it turns to this one on the left. And then a third attractor state looks like this, very complex spiral patterns, which dissipates even more energy through itself. Oh, these convection cells are also present in both the atmosphere and in the magma down below the crust. Convection cells in the magma drive plate tectonics. They move the continents around, and convection cells in the upper atmosphere, or in the lower atmosphere, actually the troposphere, is what causes weather patterns. Hot air rising at the tropics flows north and south, releases heat into the stratosphere, and then flows back down at about 30 degrees north and south, and the deserts are right there, and then flows back in this way. So convection cells are really important and useful for helping us understand how the Earth works. Now I want to talk a little bit about something called emergence. This represents an ancient adage that a whole is more than the sum of the part. Emergence is just what we call that phenomenon at this point. That is, new properties emerge at systems levels that are not fully explainable by the parts, but those system level properties are fully consistent with the properties of the parts. There's nothing mystical here. And it's fully consistent with physics and chemistry. So that's emergence and emergent properties. A good example is chlorophyll. Chlorophyll is the molecule that's present in all green things, plants and algae. It's the core of photosynthesis. It's what captures the light energy and helps transform that into chemical energy. Now, here's a diagram, a chemical diagram of a chlorophyll molecule. If you look closely, you'll see carbon, some nitrogen, some oxygen, some hydrogen, and right in the middle an atom of magnesium. And these are all linked together. Linked, it's a network. And curiously, as long as they're all linked together in this pattern, chlorophyll is green. That's because it absorbs red and blue light, but it reflects green. Plants don't use green light, they reflect it back. But curiously, green is an emergent property of this molecule. The atoms making it up are not green. And in fact, if you break the bonds in the atom, greenness goes away. So green is a simple emergent property of this system. There are way more complex examples, including emergence is a new way of looking at life and consciousness. In system sciences, life itself is an emergent property. And if you take a living thing apart, that life property will go away. Consciousness is thought to be the same. Gaia is an emergent entity. You can only think about how Gaia works as a collection of interacting parts. And so we have to understand emergence to understand Gaia, which is, of course, why I'm talking about it here. Now, there are 4 kinds of system behavior. I mentioned earlier that systems don't demonstrate just any kind of behavior, but their behavior falls into 4 classes, 1, 2, 3, and 4. The simplest behavior is what we call class 1 behavior. It's fixed and unchanging. Now, you're looking here at a simple graph. On the horizontal axis is time. On the vertical axis over here, you've got some variable x. It could be blood pressure. It could be dollars in your bank account. And you can see that the line suggests that x doesn't change with time. It's just fixed value. That is essentially death in a living system. That's the reason they call death flatlining, because it goes linear. Not much other than dead things are class 1 in nature. Class 2 is slightly more interesting. It's oscillating regularly with a very precise rhythm like this. It's a sine wave in trigonometry. 1, 2, 1, 2, 1, 2, 1, 2, over and over and over again. It's very boring, and not much in nature is class 2. Crystals vibrate on a class 2, but living systems are not class 2. Classes 3 and 4 are far more interesting. Class 3 designates something called chaos or randomness. Now, those are technically different. In the seminar I distinguished, but here I'm just going to treat them as the same. Here's an example called a Lorentz, named after the person who discovered it, a Lorentz strange attractor or a Lorentz chaotic attractor. An attractor is a notion in mathematics where you've got some quantity that is changing over time, and if you look at the graph, it appears that the quantity is attracted to a particular region in the space. It's metaphorical. It's not implying that the system is conscious. But so here's a Lorentz strange attractor. Now, what you're looking for here is a 3-dimensional graph. You've got a horizontal axis, a vertical axis, and an axis sticking out at you this way. It makes this 3-dimensional space like this room we're in. And you can imagine a single point that represents 3 different values: temperature, pressure, and salinity perhaps. And that single point is moving around in that space, representing how those 3 variables change over time. And you can see that that point is attracted to particular regions. It's the colored part, not the black part. So they call it an attractor, and yet it's not class 2 or class 1. So the people who first discovered this said, this is strange. So they call it a strange attractor. It's chaotic because that point never comes back to the same point in space twice. It's always in a different place. It's on the attractor, but it's always in a different place. Chaotic attractors are unstable, and they're usually symptomatic of disease. In us,